Hello, Machine Shop Math fans. Once again, we are back into the wonderful world of Machine Shop Math. And to quote Euclid, the laws of nature are but the mathematical thoughts of God. I think that's a neat saying. And again, I don't care what you think about God. That's between you and God. And we'll move on. All right. This video is probably going to be labeled as video 7. It'll be whatever the file V number is. Should be housed in week 3 folder. We're going to go through the 5 basic types of angles and shapes and such as that. So let's just mount our little ponies and let's get started. We'll pick red for now as a highlight. All right. The 5 basic types of angles that you should be familiar with are listed here. 1, 2, 3, 4, 5. The acute angle. Acute means it's sharp or keen. It means it is greater than 0 degrees and it is less than 90 degrees. That's acute. Doesn't mean it's pretty, it means it's acute. The right angle is 90 degrees. That angle is 90 degrees, and that's generally the symbol for 90 degrees. Obtuse. It's becoming more fat. The X, the angle, you measure the angle here like this. Oh, I don't like that color. Yeah, let's get rid of that color. Let's get rid of that color. Let's pick another color. Let's pick, I don't know, thought I picked red. Maybe I didn't pick red. All right. We measure the angle here. So that's between 90 and 180. That angle is 90, and this is less than 90 and greater than 0. The straight angle is 180 degrees. Well, hey, Mr. Wizard, that's a line. Well, very good. A line is 180 degrees. The reflex angle is greater than 180, and it's less than 360. And then a line that has an angular value of 360 is what? That's right. You got it right. It's a circle. A circle. We'll do circles in a minute. There's a radius. The distance around the circumference. All right. Very good. Types of groupings of angles. These are interior angles. Good. Here, close that out. I'm fixing to kill the internet. All right. Types of groupings of angles. Interior angle groupings. Complementary. That means this angle, this angular value of y and x equals 90 degrees. Supplementary angles, the sum of x and y, you add those two values together, you'll get 180. That's supplementary. Adjacent angles, this angle is adjacent to this angle here. So the angle BAD, that is BAD, added to angle, and I don't like the way they did this. I like going from the vertices, but that's okay. We'll get over it. All right, DAC equals the angle BAC, whatever that is. So A is the vertex, or the vertices. This right here of any angle where the two rays meet is called the vertex or vertices. All right, isn't that special? Okay, all right. Where is this at? Come over here. We'll erase that. We'll clean this up. Okay, all right. Okay, very good. All right. Okay, this is called a vertical angle. If you will read the angle, the rules of the road in the formula sheet for geometry, which I pointed out when we went through the master formula sheet. Vertical angles are opposing angles. In other words, if this angle is 45, then this angle is 45. If this angle is 30, and I'm not saying it is, I'm just saying what if, then this angle is 30. right? Okay. All right. So, goodness. There we go. Okay. All right. Get rid of that. Okay. Exterior angles. Any angle formed from extending one side of a polygon, and all a polygon is, meaning it's a multi-sided figure, poly. Like a polymer is not one kind of plastic, it's a mixture of plastics. Polygon, many-sided. The sum of an interior angle and its exterior angle will be 180 degrees. Okay, so angle C plus D, angle C plus D, if we added these two together, that would be 180 degrees. Okay, it would have to be, right, because it's a straight line. Now, this is a triangle. And the sum of these angles, the sum of all the angles inside this triangle, equals 180 degrees also, or it's not a triangle. I don't care what kind of triangle it is. All right? Okay. All right. Yeah. Okay, let's come up. So we all got that, right? This is just, you read this, it's in your master formula sheet. Okay. We'll now add the sixth type of angle, and the full angle, the circle, has an angular value of 360 degrees, and we've already talked about that. So it's really not an angle, it's a circle, but theoretically it's an angle that has a value of 360 degrees, and we will talk about circles in a moment. Again, here's another list of angles for you: the acute, the right, the obtuse, the straight, the reflex, and the full circle, or full angle, is a circle, but we don't call it that, we call it a circle. Now, if we contain three angles in a closed polygon, we have a triangle with the sum of the angles of 180 degrees. The sum of the angles in any triangle is 180 degrees. Etymology, that's a fancy word. The word polygon derives from the Greek adjective plulios, much, many, and gona, which is corner or angle. And it's been suggested that gona could also be a knee, but this is not a Jesuit program, so we're not going to learn Greek and Latin, okay? Because it's probably all Greek to you anyway. Yeah, I know, it's a bad joke. All right, so polygon means many-sided. Here's a list of some polygons, just some. There are many. Polygon is a closed figure made of line segments, each of which intersects in exactly two line segments. So, quadrilateral means it has four sides. Quad. Quadruped would be a horse. Biped would be a humanoid. Square, it's a quadrilateral having all sides equal in length and forming right angles. Okay, a square, right? So it means each one of these is a right angle, and side A equals side B. All right? Now this is two-dimensional, so we're doing two-dimensional polygons right now. A triangle is a three-sided polygon, and we already said the sum of the angles is 180 degrees, and a rectangle is a four-sided polygon with all right angles, and side B, side A, side B does not equal side A. All right. Parallelogram, there's the definition of parallelogram. A pentagon, the pentagon, a five-sided, penta meaning five. So that's a five-sided polygon, that is a penta. Hexagon is six, hex is six in Greek, hepta is seven, and octa is 8. Alpha, beta, zeta, gamma, etc., the Greek alphabet. Here are some three-dimensional shapes, just some three-dimensional shapes. We have a square pyramid. It's a square pyramid because the base is a square. It's not a rectangle. Here's a cuboid, or a cube. Okay, cuboid, because it's not a pure cube. In other words, it's a rectangular prism. It's three-dimensional. Okay, you have this dimension here, this axis, you got that, and then you've got this one coming out. And conventionally, we would call that Z, and we would call that X, and we would call that Y. Now, in week 3 folder, you'll have a video on Euclid from Khan Academy. I expect you to watch that video. It's very short. And you'll have one on René Descartes. René Descartes. René Descartes. He was a contemporary of Galileo, although he died younger than Galileo. Newton picked up where René Descartes left off and finished his Principia of Mathematica in 1690. René Descartes was in the 1650s, and he was a very devout Catholic, although he spent most of his time outside of France. He's noted for a saying, "Cogito ergo sum," in Latin, which means "I think, therefore I am." More literally, it means "I think, therefore I'm alive." What he did is he took the works of Euclid and combined the early works of algebra and came up with the Cartesian coordinate system, the X, Y, Z, which all of us machinists and long-range shooters and engineers and navigators live by. The X, Y, Z coordinate system is called the Cartesian coordinate system, named after René Descartes. Here's a torus, here's an octahedron. And why is that? Octa meaning 8, it has 8 sides, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 sides. Okay. Hexagonal pyramid, and icosahedron, pentagrammic prism, pentagonal prism, because it is 5-sided. So the pentagon, since it is not 2-dimensional, it's 3-dimensional. The one in Washington is a pentagonal prism. A triangular prism, a cube, cylinder. This is a right circular cylinder. A dodecahedron. Here is a cone, a tetrahedron, hexagonal prism, and a sphere. A sphere. Now, if you truncate this cone, if you take the top off, cut it, turn it into a funnel, it becomes a. Oh my goodness. Come on. Should use my mouse. It becomes a frustrum. And there are 2 types of frustrums that we'll be dealing with. Mostly with the conical frustrum. It's right circular frustrum and a rectangular prism frustrum. You see frustrums a lot in machining and engineering. A funnel is a frustrum. The injection mold for the rectangular 3-dimensional trash cans are a frustrum. It just means that this diameter here is smaller than this diameter here. Or this square here is smaller than that square there. Now, you have 2 formulas for these. One for a rectangular frustrum. It's in the volume sheet, which precedes this. And one for a right circular frustrum. If it's round and your formula does not have pi in it, then you're going to cry because you're going to get the wrong answer. If it's round, it must have pi. If it's round, your formula must have you must have pi in it somewhere if you're going to find the area or the volume of it. Enough said on that. All right. These formulas are up in here. No, they're not. They're past it. You would think I would have already had this planned out, didn't you? There's your frustrum. So let's get past the triangles, the circle. Here's your principles of plane geometry, the rules of the road for geometry. Here is your formulas for areas. We will talk about those later. Here's your formulas for volumes. Your Foostrum for a right circular cone is here. You'll notice it has pi in it. Pi is right there. And you'll notice that the Foostrum for the volume of a regular pyramid does not have pi because it's not round. And you're dealing with radius here. Okay? We'll work some more of these out later. All right. We'll work more of these out later. Okay, let's go back up. Okay, so that's your Foostrum. Sounds good to say, doesn't it? It sounds like something your mother would slap you for saying at the dinner table. You see a lot of Foostrums in industry. Hoppers on silos. I've designed structural steel Foostrums where they were like 20 feet across the top, 8 feet at the bottom, or 4 feet at the bottom, and they were really tall. And they go down the bottom of a silo, so the grain filters through here into a pneumatic opening to regulate grain or silo stuff and put it on a conveyor and it ships it out. So you see a lot of this stuff in engineering and industry. Okay, triangles. What do we know about the triangle? The triangle is three-sided. The sum of all the angles is 180 degrees. 180 degrees. Right? So in this case, this one is 60, 60, and 60. It's an equilateral triangle. All three sides and all angles are equal to one another. So 60 times 3 is 180. Over here, moving from left to right and then going back down. This one's an acute triangle. Just like an acute angle, all three angles are acute, which means what? They're less than 90 degrees. Okay, so in this case, I think that's 62, 75, and 43. Add those up, and you should get 180 degrees. Let's see, that's 105, and 105, and 75 is 180. All right, good. At least something's working today. All right. Isosceles triangle. The isosceles triangle has two equal sides. These two sides are equal. That side's equal, and this side's equal. And this side, the base, is not. And it has two equal angles. So, this angle here and this angle here would be your equal angles. Scalene triangle, it has no equal sides or angles. All the sides are different lengths and all the angles are different. There is a formula called Heron's formula. Heron taught at the University of Alexandria in around 60 to 70 AD. Euclid taught at Alexandria in about 300 BC, and along around 70 something AD, Heron was 70 AD. If I said BC, that was wrong. It's 70 AD. The Romans decided to burn the library of Alexandria. Why? No one really knows. The Romans just did stuff like that. Had it not been for the Arabic-speaking peoples who got everything they could get their hands on and headed deep east, so the Romans couldn't find them, we would not have had the works of Euclid, the equal sign, or any of these works of Heron. Heron also developed the first working jet steam engine called the Aeoliophile, and they thought it was a toy. Nobody connected the dots to connect a belt to it to make it do something. But Heron also used hydraulics, pneumatics, and steam-driven stuff to open and close temple doors so it would make people go, woo, the gods are helping us open doors and stuff like that. So anyway, enough of that. So Heron's formula will give us the area of a triangle, and it's in your formula sheet. if you have a triangle with 3 unequal sides. So if you have a scalene triangle. All right, the right triangle is, well, we'll go to the obtuse triangle, and then we'll go to the Mac Daddy of triangles, the right triangle. So obtuse, it has one obtuse angle, okay, 130 degrees. It's greater than 90. It's less than 180. If that's 130, we don't know what these are here, but the sum of these two angles has to equal 50 degrees, right, in order to get 180 degrees. So if this angle was 30 degrees, if that was 30 degrees, then this would have to be what? It would have to be 20 degrees, right? If that was 130. So 20, 30 is 50 plus 130 is 180. Okay? That's pretty easy. You all have this. Now we get to the Mac Daddy of triangles. The right triangle. This is the Mac Daddy. With the right triangle and the Holy Trinity of trig, sine, cosine, and tangent, you can do just about anything. You can reconstruct the world. Now you'll notice that a triangle with a side ratio of 3, 4, 5 is a right triangle. Remember, the sum of all the angles is 180 degrees. So this is an old carpenter's trick, old pipe layer's trick. If I got a right triangle, and if I want a triangle that's right, the hypotenuse, which is across from the right angle, from the 90-degree angle, is called the hypotenuse. The hypotenuse. And this is side C, and this is side A, and this is side B. And sometimes I'll write the sides so you don't get the angle A and angle B and angle C mixed up. Side A is always opposite angle A. Side B is opposite angle B. But a ratio of a 3, 4, 5 triangle is always a right triangle, always. Now, Pythagoras of Samos, he lived about 570 to 495 BC, was an ancient Ionian Greek philosopher and the epitomous founder of Pythagoreanism. He was also an automaton. They had the concept of the atom, and long before Einstein or Madame Curie, the idea of subparticles that no one could see, and they called them automatons. Here's the Pythagorean theorem. It only works for the right triangle. Only for the right triangle. Only for the right triangle. Only for the right triangle. C squared equals A squared plus B squared. Now, because I'm such a nice guy, I algebraically rearrange these for you so that if you know side A and side B and you want to solve for side C, here's your formula, assuming it's a right triangle. If you know side C and side B and you want to solve for side A using Pythagorean's theorem, here's the formula you use for that. If you know side C and side A and you want to solve for side B, this is the formula you would use for that. Okay? All right. Only for the right triangle. Now we get to the circle. The basic circle. Notice our XY coordinate system. I put the Y down here because it was going to get confused up here. I guess I could have put the Y up there and the X right here. Now, Rene Descartes established that the horizontal axis was X and the vertical was Y. These things can be rotated around. If this was a conventional milling machine, the vertical would be Z and the horizontal would be Y, X, and the in and out would be Y. So you can arrange these around. But the conventional two-dimensional is X and Y. And our coordinate system is always X, Y, and Z. In 2 dimensions, it's just X and Y. So X is always first, Y is always second. So at the center of this circle, since we haven't located it anywhere on the planet, it's 0, 0. Now, if we move this into a part, and this dimension or this location became, I don't know, 10 and 10, then everything else would change, okay? So, all right, but for right now, it's at 0, 0. So that's 0x and 0y. If it's a 1 unit radius, and we'll just say this represents an inch. It could be a foot, could be a mile, could be a light year. That'd be weird. But anyway, let's just say it's inch. So radius is 1. Then that means this coordinate right here is on an x of 1 and a y of 0. Up here, it's a x of 0 and a y of 1. Over here, it is a y of 0, but an x of negative 1. So we go negative 1 units here. We didn't go any on the y, so this coordinate point is negative 1 to 0. This coordinate point down here is, we're not talking about an angular value of that point, we're talking about the coordinate, a 0x and a negative 1y, okay? Now r is the radius, d is the diameter. The diameter is twice the radius. The diameter is this distance all the way across here. So in this case, if radius is 1, the diameter is 2. That's this distance here, all the way from there to there is 2, because the radius is 1. Okay? Now, pi. Pi is a constant. It's on your calculator. It's got a little funky little symbol there. Pi is a relationship. It is the ratio equivalent. It doesn't have any dimensions to it, of the circumference, which is the distance all the way around the circle. You start here at 1, 0, and go all the way around and end up right there. Full 360 degrees, that's the circumference, the linear distance. If you took a tape measure and wrapped it around that pipe or that circle, then that would be your circumference. The diameter is the distance across through the center. So if you divide the circumference by the diameter, you get pi. And pi is a constant. Okay? So pi is the circumference divided by the diameter. That's a fraction again. It's a relationship. All right. All right. The area of a circle in units squared. Anytime you talk about area, it's units squared, units raised to the 2 power. Okay? We'll talk more about roots later. It's either inches squared, feet squared, yards squared, miles squared, light years squared, whatever. Okay? The basic formula, it's up in the formula sheet, for the area of a circle is pi r squared, or it's the area of a circle is pi d squared over 4. Where A is the area and units squared, whatever those units are. Could be meters, could be millimeters. R is the radius in the same units, meters, feet, inches. Diameter in the same units, meters, feet, inches, millimeters, whatever. Have to be the same units. The distance around the outer edge is the circumference in whatever unit you're in. Linear dimension, inches, feet, etc., millimeters, whatever. Okay, I think you get this. So here's a rearrangement of the formula. We already said that pi is c over d, yes? So if we algebraically rearrange this and we know what our radius is, we want to know what our circumference is. It's 2 pi r is the circumference. Now this isn't squared. These aren't square units. This is an area. This is a linear measurement. Or it's pi d. And it goes back to pi equals c over d. So this is the algebraic rearrangement, okay, for that ratio, that relationship, okay? Now, circles are measured in degrees and radians. And when we get to trigonometry, if we have time, and we probably will, I will give a dissertation in video on to degree or not to degree, to radian or not to radian. Now, some people claim, some mathematicians claim that radians are more precise than minutes of angle, and I disagree. We will discuss that when we get to trigonometry. But your circle can be measured in degrees, minutes, and seconds. We will have an exercise on that. Or it can be measured in radians. So 360 degrees, so if we started at 0 and went all the way around the circle, back to 360, it would be the equivalent of 2 pi radians. So 180 degrees, which is half of 360, is pi radians. And you can see how the circle is divided. 30 is 1/6 of 360, so it's pi over 6 radians, pi over 4 radians, et cetera, 45 degrees, okay? All right, and then we go over here. That would be 180 is pi as you go around. We will be dealing mostly with degrees. In fact, we'll be dealing totally with degrees. But we should have time in this 8-week course. I'll do a video on to degree or not to degree. And when we get to trig, and you will find that if you can split the angle up in degrees, minutes, and seconds, degrees, minutes, and seconds, you'll have a chance of having a more precise output than with just radians. All right. But we're talking about the angular value now of this line. We're not talking about the length of the line. We're talking about this angular value. So what's the angular value? Well, this particular point happens to be 30 degrees. 30 degrees. The angular value for that one is 45 degrees. And the angular value for this one is 330 degrees measured back, way back to here, boink, right? And this angle is 30, okay? So 30 minus 360 gives you the angle. We measure it from 0 going counterclockwise, all right? So I probably should make this a little nicer. Okay. So the angular value of this line is 330 degrees. And that would be the angular value of that point. Not the coordinate, but the angular value. Where does that point lie angularly along the circumference of that circle? We'll deal more with this later on. Here's a typical circular protractor, X, Y coordinate system. Now, if we were going to do 3 dimensions, we would have Z or Z coming out something like this. But we're not. We're dealing just in 2 dimensions right now. And so that is redundantly moot at this point. Okay? All right. How long is this video? Oh, we're at 33 minutes. Man, it's a terrible death to be talked to death. All right, so here are your rules of the road. The sum of the angles of any triangle is equal to 180. So you read through all of these. These are your geometric laws, if you will. Okay? And here's your formulas for area. And here are your formulas for volume. Now, volume is always going to be in units cubed. Volume is units cubed. Because volume is dealing in 3 dimensions. So oh my God. Wow, that's ugly. Let's make a square. Okay. Now, right now, we just have 2 dimensions here, right? Just 2 dimensions. Okay. I don't have my paint palette up, so we're just going to use this. So this is 2 dimensions. Okay. This is side B. This is side A. So if I wanted the area of this 2-dimensional figure, I would just go A times B. And whatever our answer is, it's going to be in units squared because it's area. Now, if we add a third dimension, whatever that third dimension is, let's say we take a third dimension out here. Oh, that's almost close. And this is going to be side C. And we want the volume. All we do is have to take the area and multiply it times the third dimension. Now, we're assuming, of course, this is a right polygon, a prism, a right prism. So we would take now A times B times C, and that equals our volume in some kind of units cubed, right? Because we have these units times these units times these units, right? So we have units times units. So if we had inches times inches, that would be inches squared, because we're multiplying the same thing by itself, so it raises it to the second power. And then if we multiplied that times another inch, then we got inches times inches times inches, and that gives you inches cubed. And how do you undo that? Well, you take the cube root of it. So if we had inches squared, and I took the square root of that, I would be back to inches. And then if I took the cube root of inches cubed, I would get inches. Okay? All right. All right, we'll deal more with these as we get into it. And then here's trigonometry. That's the dry one out of the book. This is the one that Uncle Mikey, your instructor, did for you, Trigonometry Expanded. And I did all of the algebraic rearrangement, and we'll talk more about this later. All right, so we are at 37 minutes on this video. And again, I do believe this is going to be titled Video 7. It'll be in week 3. Kind of gives you an idea of the angles, shapes, and circles. All right? Now, you understand the holy trinity of trig, sine, cosine, and tangent, and understand that right triangle and how to manipulate a circle. And you're going to be one powerful machinist. One powerful machinist. All right? All right. So that'll be enough for this video. We'll see you on the next one.